And I'm a prof in 2 different departments, and this is actually kind of crucial to the theme of my talk tonight. So I'm in the Department of Physics, which is where the astronomers live at McGill, but I'm also in the Department of Earth and Planetary Science, and that's because I study planets. I mostly study planets that are really far away, so I use astronomical tools to try and understand how they work, all right? I'm also part of these 2 institutes, so I figured I'd give them shout outs because they give me money sometimes. Okay, here goes. So let's start very, very close to home. Okay, so the very first planet anyone explored was Earth. And we understood it by basically starting on a very local scale, by poking around, scratching rocks, trying to understand patterns, the kinds of rocks people could find in different locations. All right, so geologists were really the first, planetary scientists. And so geologists started by studying the rocks they could find around their homes, and eventually, over time, started noticing patterns in the kinds of rocks they could find, right? And so you could make a map like this, a geological map, showing where you find certain kinds of rocks for all of England and Wales and Scotland, in this case. All right, and so this was sort of the birth of doing a little bit more than just the local science, but actually starting to understand something a little bit deeper about how the planet worked. All right, but it doesn't really become what we would call planetary science until the modern era, okay, where you can make a map that looks something like this, which is truly global, and you can start talking about things like plate tectonics. All right, and so at this point, this is basically planetary science. Some people might call this geophysics, but really, to me, you're studying planets. Okay, it happens to be the planet we live on. We have really good observations of Earth, but eventually, we're going to have observations like this for loads and loads of other planets. All right, so this is really the birth of planetary science. Okay, and I could give you a similar series, a similar sequence for how we study the atmosphere. Right, it started with people noticing patterns in the local weather. Right, so they'd say, well, this place in England, just to stick with that theme, this place in England, it's like typically rainy in the summer, and this place, it seems to be rainy at some other time of year. Or maybe you would notice a pattern, like when my buddy said it rained over there a week ago, or not a week ago, let's say a day ago, yesterday, the odds are that it's going to rain here today. And so you start noticing correlations in the weather, right? And eventually you start sending ships around in the ocean and you start measuring the temperature at different locations. And again, you start noticing patterns. You start noticing patterns based on the temperatures at different locations, the wind directions, all right? And you start building up from meteorology, so the kind of local weather patterns, to climate science, where you're understanding really macroscopic things on our planet. How does our planet move heat from the equatorial regions, which are hot, to the polar regions, which are cold? All right? And so on Earth, this is the kind of narrative, right? Is we've always understood what's going on locally first, and then eventually over time, by talking to other people, other scientists in other countries, or people who traveled broadly, eventually you can start piecing together the jigsaw puzzle and understand how our whole planet worked. Okay, so it was always local first, and then eventually global. But Earth is the only planet we can do that for, right? Because Earth is the only planet we've ever lived on. And so every object, planet, moon, whatever, every other object in the universe that we will ever study, we're always going to be studying it in the opposite direction. We're always going to see it first as a speck, and then we're going to zoom in, we're going to see kind of like a ball, and then we're going to start talking about the gross properties of that ball. How windy is it? How cloudy is it? What color is it? Those kinds of things. And then we're going to zoom in, zoom in, zoom in, and eventually people will be talking about geology on these other planets. Okay? But for someone who's familiar with Earth science, this is completely backwards. Okay, so the study of every object other than Earth is kind of, in a way, backwards. We're starting with the global view first, and then, if we're lucky, we can zoom in. So, the nearest object to us, other than the Earth, it's not a planet, but it's close enough, is the moon. All right, and so the moon, people first started studying again by staring up at it. And you stare up at the moon, and what do you notice? Well, you notice there's some huge craters. You notice there's some bright spots. There's some dark spots. And that was really the study of the moon for hundreds of years was just limited to the fact that there were dark spots and there were bright spots. And then, if we're lucky, we can zoom in. But then, eventually, humans were able to go to the moon. Okay, who here was alive when astronauts were on the moon? right? So the moon, people first started studying again by that's kind of pathetic, isn't it? And I don't mean pathetic because I'm not dissing your age or anything. I'm just saying it's pathetic that we haven't been back, right? Like I was not alive during any of the Apollo missions. Okay, that's kind of sad. But then, eventually, and the fact that we apparently would actually be very, very difficult for humans to go back to the moon now. It's not even like something like, yeah, we could do it if we tried, but we don't really want to try. We'd rather, you know, fight wars and stuff like that. It's not even that. It's like actually technologically very challenging to go back to the moon. A lot of the people who have the brains, the expertise to do this are dead, right?
We don't have a mortal enemy.
I was not alive. We don't have a mortal enemy. This is true. Okay, that's kind of sad.
So anyhow,
the fact that we apparently would actually because of the mortal enemy, among other things, and some real cojones, we don't really want Americans managed to get to the moon, fight wars and stuff like that. Right? And so they were able to study. And to be fair, the first astronauts who went to the moon were more interested in you know, kind of political posturing, and then there were some who were into golfing and stuff. But eventually, thank goodness, they actually sent a bona fide geologist to the moon. And the geologist had a field day, right? Because this is what geology is all about. And also, you know, geology says geo, which means earth, but, you know, whatever. Geologists are sort of equal opportunity, and so they said, hey, this is the moon, it's got rocks, I can study rocks. And so a geologist versus an astronaut, very, very happy astronauts. So there's a, you know, political posturing, right? And so the moon is actually the only object other than Earth that a geologist has ever gone and studied. And that, again, should give you pause, right? Because as the evening wears on, and I keep talking about further and further world, you have to take everything I say with a big grain of salt, okay? Because this is the most distant place that a geologist has been to. We sent one geologist to one spot, and he picked up some rocks, quite a few rocks actually, brought them back to Earth. People have studied those, but that's it, right? And beyond the moon, nothing. The only object other than, all right, beyond the moon, the best we've done is this. We've sent a robot. We've sent lots of robots to Mars. A lot of robots. Okay? And a robot is great, but it's no geologist. Okay, so for starters, the robots are very timid. It's not so much that they're not scaredy cats, it's just that the people who control them are scaredy cats, because this mission costs billions and billions of dollars. Okay, so if you're the moron who accidentally makes Curiosity get stuck in a crack somewhere that it can't get out of, you're in deep trouble, okay? And I've worked with my fair share of rocket scientists and NASA engineers, and they're very, very conservative bunch, okay? And so that really sets a limit on what you can do with something like a rover. Okay, you can explore around, but it's very slow, right? Just communicating with your rover back on Mars takes a long time. Mars is far away, okay? Even at the speed of light. And so you can't do rapid reaction things. You can't say, oh no, I'm losing my balance, let's change something. No, if you lose your balance, your rover tips over, stop, finish, no more mission. All right? So this is the best we've done other than the moon. We've sent robots. The robots have returned some interesting data. We now know pretty darn well that Mars used to be wet. That's exciting. There are rivers on it. Might have been an ocean or a sea or something like that. It's debatable. There was definitely liquid water on it. There might even be some water hidden underneath the surface. There certainly weren't canals, and there wasn't the kind of life people read about in the magazines. Okay, all of that stuff was shot down by the Viking landers. Right? The first lander we sent to Mars basically shot down all the fantasies people had. Okay, it was a very sobering moment. And it was essentially the death of the first wave of astrobiology. Okay, so until then, people had been really optimistic about finding life elsewhere in the universe. And then after the Viking landers, everyone was really depressed. And then for a long time, people just said, well, I guess our only hope is just to listen. We're just going to listen for aliens. Okay, and that was essentially the history of astrobiology for a long time. But we'll come back to that thread a little bit later. Essentially the death. Okay, so here's my sort of sober statement. Note I'm saying in my lifetime, so we will not send astronauts beyond Mars in my lifetime. Okay. Some of you, I noticed there's a few very young people in the audience. You might still be around and go beyond Mars, but I don't think I will. Okay? And if I had to bet on it to go back to the theme of the mortal enemy, my guess is that the first person on Mars is probably going to be a Chinese woman. And so it will be a fantastic moment for all humanity and for science, and hopefully we'll get the fire burning again in the rest of the world. Okay, so we can't send astronauts, well, right now we can't even send astronauts back to the moon, but let's say even during my lifetime, we're not going to send them anywhere past Mars. So what do we do to learn about planets beyond Mars? Well, we send probes, okay? So probes are kind of like the Mars rovers, except they don't have wheels, right? They're just flying through space. And so they're flying along through space, and then they snap pictures of things that they fly by. That's basically what a typical NASA mission is. A typical NASA probe. And so here's the Cassini probe. Went out to Saturn. You know Saturn. I mean, this is a cartoon, obviously. But because there's no one hanging out there to take a picture of Cassini as it flew by Saturn. So that's a cartoon. But this isn't. Okay, this is the real deal. This is a picture that Cassini took. Okay, and this is striking for a number of reasons. One, it's just gorgeous. Right? Two, this is a view that we could never see. Even the biggest telescope we have on Earth could never possibly see this. Why not? Hanging out there to take a picture of Cassini as it flew by Saturn. Yeah. You're looking at the dark side. You're looking at the night side, but this isn't of the planet. Okay, you're looking at the night side of Saturn. Okay, Saturn is really, really far from the sun. So whenever we look at Saturn, we always see basically the day side of Saturn. Okay, so this is a really precious view of the planet. All right, this is a view you can only get not by building a really big telescope. You can only get this view by actually sending a probe out to that planet. All right, and so we've learned a whole bunch about Saturn from, again, just flying by, taking pictures, measuring, you measure magnetic fields, you measure cosmic waves, you measure things, you take pictures, you get spectra, and that's essentially what planetary science is all about. Okay, so this is a really now, with Cassini, we also got the Huygens probe, right? And that was a probe, that was a European Space Agency lander that went down on Titan, okay? And so this is pretty awesome. These are snapshots of what it saw as the Huygens lander was coming down through the atmosphere of Titan. Now, it's pretty crummy resolution, which is okay, because it's from, not quite a planet, but still a largish moon, very large moon, actually, orbiting very, very far away from us. Right. And this is, as it's coming down through the clouds, you're going down, and you actually start seeing mountains and rivers and lakes. Okay, on Titan, and so that's pretty cool. This is the only planet that we know of that has loosely a hydrological cycle. It's not hydro, it's not water, but it's a liquid nonetheless. Okay, so in this case, it's things like methane, butane, the kind of stuff you burn in your camping stove. So that's what flows on this planet. The planet is so cold that instead of just vaporizing, that stuff flows. And the stuff that's really hard, those mountains, the things that are basically hard like rock, are actually made out of ice, water ice. That we know of, okay. Kind of a weird world. Loosely a hydrological cycle. Okay. It's not hydro, it's not water. As far as landers go, that's as far as we've gone. Okay, so we landed something on Titan. It was pretty impressive. It took some pictures. Turns out if you change the colors a little bit, it doesn't look that dissimilar from Mars or the moon. It's kind of a bunch of rubble, right? You start realizing when you explore a lot of these worlds how special our planet is. Right? If you were to land on our planet, unless you got really, really unlucky and landed in some parts of like Antarctica maybe, or a few other places on Earth, maybe high in the Atacama Desert in Chile. For the most part, if you landed on Earth, it would be painfully obvious that this is a really exciting planet with lots of cool stuff going on. It turns out if you change the colors a little bit, other planets, you see some cool geology, you see stuff that might get you excited if you care about rivers and mountains and things like that. But if you care about life, which I think we are in a life science building here, so if you care about life, this planet is no good for you. Or a few other places on Earth, maybe high in the Atacama Desert in Chile. All right, keep chugging away. We're getting further and further from Earth. Voyager 2. Okay, this mission, we're almost going back in time, right? Again, this is one of those depressing moments, like the astronauts on the moon, right? So Voyager 2 did a flyby of Uranus and Neptune. And these are still, if you look it up anywhere on like Wikipedia or any other place, these are the pictures you're typically going to find for these planets. And it's because they're the best pictures we've got. Right? We've never sent anything back to the ice giants.
We're getting further and
Right? See, these are planets here in our solar system, and we have these images. We have 2 snapshots from the Hubble Space Telescope.
Again, this is one of those depressing moments.
But for the most part, we don't really know much about these planets. Okay? There's talk now going out and trying to explore these planets better, because it turns out these planets are the closest analogs we have to the thousands and thousands of planets we've discovered around other stars.
These are the pictures you're typically going to.
But I'm getting ahead of myself.
So
So that's Uranus and Neptune. Some of you may recall in the old days there was another planet.
And we have these images. We have
Remember that planet? Yeah, Pluto. So there was this mission called New Horizons. It was sent out to go to Pluto, and Pluto got demoted. So it was still on its way to Pluto, but now Pluto is merely a minor planet, a dwarf planet, a not quite almost pseudo planet. And so New Horizons eventually got to Pluto, and of course it took some pretty awesome pictures. These are the kinds of things that if astronomers had seen these before demoting Pluto, it's not clear that you would have demoted Pluto, because you see it and you're like, hey, it's a spherical thing, but then you zoom in and you get shots like this. Again, these are really special images, right? Because of that same angle. You're way far from the sun, looking back,
and of course, it took some pretty
over
awesome
the
pictures.
tops of mountains.
These are the kinds
Back
of
towards
things
the sun, out at Pluto, right? You can only do this by sending a probe out there, right? This is something that costs, like, at a minimum, we're talking like $500 million to $1 billion.
You see it and you're like, hey,
There's no way around it. Because you have to launch and it's got to climb all the way out of the sun's
you get shots like
gravity,
this again.
right? All the way up to where Pluto is.
These are really special.
Right, so again, mountain chains, things that almost look like rivers, which is totally obscene because this planet is so cold that, I mean, what could possibly be liquid there? But it turns out if you look above it, you can see these kind of weird lines. Okay? There's actually a little bit of an atmosphere. Pluto has a little bit of an atmosphere. It's actually got hazes. You can see layers of clouds in there. It's crazy. Okay? If people had known this, who knows how the IAU would have voted. Okay. Pluto's got a friend, Sharon. The New Horizons got pictures of that too. Okay, I think this is the last of my depressing statements. It cost a lot of money to send something out to Pluto, and Pluto was actually a planet. And now, because of the way the names have changed and stuff, it's really unlikely that someone will discover a new planet out where Pluto is, let alone beyond Pluto. Okay, and so it's unlikely we're going to get the kind of the political motivation to send out another probe even further away. Okay, and it would cost a lot of money.
Okay,
right? It just costs a lot of money to send statements. And the problem is, the more juice you give them to go really fast, the faster they fly by your planet. So you really get diminishing returns. I mean, eventually, if you want to send a probe really far away, you want to send a probe to like Alpha Centauri or something, your probe is going so fast by the time you get to Alpha Centauri that you kind of say, hi, and that's it. And so you don't get to stick around, right? If you wanted to stick around, you need fuel to slow yourself down. But the problem with fuel is that it weighs something, okay? And so that means when you launched, you needed a bigger booster to get you going fast, okay? And then you get this vicious circle, this vicious cycle, okay? And that's the fundamental thing, the fundamental equation of rocketry, right? This is why it's really hard to launch big payloads. Okay? The military are good at it because they're interested in killing people. But for science, it's hard for us to get big payloads into space. Okay. You needed a bigger booster to get you going fast. Yep, that's right. Yeah, you can slingshot off of planets and do other trickery. Okay, here's a planet that would be kind of cool. If we were to send a probe, this would be a good planet, a good target. Okay, because this is a planet that may exist. Okay, this is Planet 9. For those of you who aren't complete astro geeks. So Planet 9 is a hypothetical planet. Honestly, at this point, I'd give it maybe 1 out of 4 odds of actually existing. But it was a planet that was hypothesized to exist earlier this year because of this. Okay, let me explain this. Here's a planet. So the purple lines are orbits of known real objects. These are ice balls. You can kind of think they're almost like a comet, except they're not coming close enough to the sun to get that pretty tail. So they're just an ice ball. Okay, and so each purple line here is a known pretty largish ice ball. Okay. And what people
It was a
noticed,
planet that was
they discovered a lot of these ice balls.
earlier
Actually, the
this
person
year.
who's discovered a lot of these
Because of this.
is the same Mike
let me
Brown who
explain this.
famously killed Pluto by basically demoting it. It turns out some of those ice balls are actually bigger than Pluto. And so this is actually why Pluto is no longer a planet. It's precisely because of these ice balls. So the point is, what a number of people noticed was that these ice balls had these elliptical orbits, really stretched out pretty large orbits that were mostly, you know, if you kind of squint, they're kind of pointed in the same direction, they're kind of pointed to your left. Okay, and so then they did some computer simulations for how planets orbit, and they deduced that you could explain this all perfectly well if there was in fact a planet, which they call Planet 9, as opposed to what they used to call it, which was Planet X, right? Why did they call it Planet X? Because it was the 10th planet, right? And if you've seen enough, Rocky movies and stuff, you know X is 10. And so they used to call it Planet X, but then when Pluto got demoted, then you didn't need the 10 anymore, and so then they dropped it back to Planet 9. And they deduced that. So here we go. That's the orbit of Planet 9, the hypothetical best guess orbit of Planet 9. It's that orange thing. As opposed to what they used to. The point is, it orbits really, really far away. Like everything you know of in our solar system is crammed into that little white area in the very center there. Even the ice giants, Uranus and Neptune, everything is crammed right in there. This is planets really, really far away. Okay, so how could we possibly detect Planet 9? Okay, we're not going to send a probe to it. We're not going to send humans to it. We're not going to send a rover or any of that stuff, right? We don't even know where to look. It's that orange thing. So now we get to talking about telescopes. Really, really far away. Okay, we're finally gone from the realm of what people would traditionally call planetary science, which is usually means you send like a rover to it, or you send like a probe that flies by the thing. And now we're going to talk about telescopes, which means the thing's too far away. You just completely punt on going out to where that object is, and instead you build a big spyglass and you just look at it from far away. Okay, and if you want to look at it better, just build a bigger telescope. Okay, so this is the realm of astronomy. We get to talking about right. We build big light buckets. We count up lots of photons. That's basically what we do for a living. So this is a Subaru telescope in Hawaii, and so this is one of the biggest telescopes, and it's very well suited for looking for a planet like Planet 9. Okay, and that's because it's got a very wide field of view, so you can actually survey big chunks of the sky. Okay, in one go. And that's useful if you don't know where to look. Okay, most telescopes, so a lot of you don't know this, but most professional telescopes, things like the Hubble Space Telescope, are actually very, very small field of view. It's like lots of tiny little things. That's what we do for a living. Okay, and that's because we're looking at things that are so far away that we, something like that is totally fine. But if you don't know where to look, you want wide field of view. So Subaru is pretty good for looking for Planet 9. This is an alternative way to look for Planet 9, okay, is instead of looking for the little dot, so looking for light that's bounced off of Planet 9, instead you can actually look for the heat signature of Planet 9. Okay, and so this is a telescope that could do that. This is the Atacama Cosmology Telescope, ACT. Okay, it's in the Atacama Desert, down in just off of the Andes in Chile. So Subaru, and it's basically, it's not quite a radio telescope. It actually detects millimeter wavelengths. Okay, so things that are about the thickness of your fingernail. Okay, so that's the kind of wavelength for those of you who are used to the electromagnetic spectrum. So this is a telescope that could do that. So this is radiation you can't see. It's very, very red compared to what you can see. Okay, but in principle, you ought to be able to detect the glow of this planet, of Planet 9. Okay, it should still be glowing from when it formed 5 billion years ago. It's not quite a radio telescope. Okay, and that's it for what we've got in our solar system. Okay, and I'm even loosely including Planet 9 in here, which probably doesn't exist. Okay, so what about planets around other stars? So this is radiation you can't see. Well, what about? Well, there's a lot of them. Okay, so in case you've been living under a rock for a while, it turns out the vast majority of the planets that we know of don't go around the sun at all. They go around other stars. Okay. All right, and this was true even back when I was in grad school. Okay, and I'm even loosely when we demoted Pluto. Probably doesn't exist. Okay, and people were very sad. There were letters. What about planets around Congress people and stuff like that? I mean, it made no sense, right? Because people were writing about one planet, and at this time, it's hard to tell on the scale, but we already found about 100 planets orbiting other stars back then. Okay, and so to people like me who studied those planets, I was like, how can you possibly care about Pluto? It's so small. It's like so still barely a planet. Whereas these things are for sure planets, and there's hundreds of them. Okay, and now the numbers have climbed. They're close to 6,000 now. Okay, number of planets discovered around other stars. Okay, and you can see there's a big spike at the end there. That's largely due to this one NASA mission called Kepler. Okay, Kepler was very good at finding planets, so Kepler gave us a big bump there. But even without Kepler, there's a gradual steady rise, and now we're going to follow up Kepler with a bunch of other specific planet hunting missions to go and try and find more planets, and in particular to find closer planets to us. Okay, so you want to try and study one of these planets. You want to see this planet, right? I would love to be able to show you a picture of these planets, and I can only do it for a very, very few of them. Okay, and the problem is this. Okay, trust me, there's a planet orbiting that star. But even with the best telescopes, the biggest telescopes, even with the Hubble Space Telescope, whatever, you stare at that star, and all you see is the star. And that's because the star is really bright. Okay? Okay. So it's anywhere from like 1,000 to 1,000,000 to 1,000,000,000 times brighter than the planet orbiting next to it, depending on what kind of planet we're talking about. Okay? So it turns out it's actually extremely challenging to try and block out the starlight without blocking out the planet orbiting next to it. But a few brave people have managed to do it. And they've used some of the best instruments on Earth, right? So Keck Telescopes. And so here is maybe the only image I'm going to show you of a real planets. This is like a real picture of extrasolar planets. Okay, and there's a nice local connection here. So it turns out it's actually extremely PhD at the University of Montreal. He's now over outside of Victoria at the Hertzberg Institute for Astrophysics. And so just Salma was the first person to discover telescopes. Planets using the direct imaging method. Basically, he discovers planets by blocking out the starlight. Image I'm going to show you kind of ratty hole in the middle is actually there used to be a star there, and he's managed to kind of block out the starlight and remove it. Okay, using a variety of clever tricks that I can explain later if you're interested. And then what's left, those 4 dots that are labeled B, C, D, and E, and so little arrows, those are planets. Those are actual planets. And you're seeing again the heat from these planets. You're seeing the thermal radiation from these planets. Okay. And so this is really exciting. It turns out it only works for the system for a couple of reasons. One, these planets are extremely far from their star. Okay, so there's, for those of you who are trying to use again later, 20 astronomical units, and then so the distance between the sun and the Earth is 1 astronomical unit. So you can see these planets, like planet B, little arrows, those are planets. Those are 100 astronomical units. There's nothing in our solar system orbiting that far. And these are giant planets. These things are bigger than Jupiter. So this is really exciting. Okay, so this only works because A, the planets are just crazy far from their star, and B, because these planets are big and they're hot. Okay, and so you can actually see the thermal heat coming off these planets. Okay, and so with modern technology, we still can't actually see something that looks like our solar system. We can't see our Jupiter out there. Okay, you wouldn't be able to see the faint blip of light next to the sun. But we're working on it. And so here is a mission, WFIRST, which is an acronym. It's the Wide Field Infrared Space Telescope. And so this is a mission that NASA is going to launch in early 2020. Okay, and the WFIRST mission should be able to actually see Jupiter. Okay, maybe see Saturn around nearby stars. Okay, so we're going to get to a point where we can actually start seeing the light from nearby planets. So here is a mission. So that's exciting. But what everyone really wants is something like this. Right? You want to see an image where you block out the starlight and then you see these dots. And one of those dots is a Jupiter. Okay, that's fine. It's not that we don't like Jupiter, it's just that what we really care about are planets that are smaller and cooler than Jupiter. We care about things that are more earthy. Right? Saturn. Jupiter's there, but then notice the other dots. You've got Earth, the pale blue dot, and you can see Venus also. So here is a mission. That's exciting. This is the kind of image we want to be able to take. Okay, for at least the nearest stars, the nearest, say, 100 to 1,000 stars. We want to be able to take images like this. Okay, if we can take images like this, then we can look at that pale blue dot, and you can see how the colors change with time as the planet spins around on itself, and you can do neat things. right? You can start mapping out continents on that planet. Okay, it's not that you're actually seeing the continents on the planet. You're just inferring that there are continents because the colors of the planet are changing in a very regular way, and you can use some map to figure out what the planet looks like. All right. So this is the kind of stuff we want to do, but to do it, we need a really big telescope in space. Okay, and so in order to make those kind of even very rough maps of Earth, right, you can start mapping something like this on that planet. Okay, it's not that you actually call the high definition space telescope. You're just inferring that there are continents because the colors of the planet large aperture space telescope, also known as to figure out large UV optical IR. So this is the kind of stuff we want to do, but to do it, the point is we need a really big telescope. It's about 11 or 12 meters across. Some people want to be 16 meters across. That's enormous. We're talking about something that would fit in this room, but not with any of you in it, right? So if you all just got out of the way, we could plunk down the telescope, just the mirror in here. The telescope itself won't actually fit in at all. So that's a problem, right? Because if you think about how you're going to launch this thing into space, it's quite challenging. And so your options are either one, you fold it up like origami. Okay, that's actually the strategy we use with the James Webb Space Telescope. I'll talk about later. You can fold it up. That works okay up to a certain extent. Or you launch it in pieces and then you build it like Lego out in space. Okay? That happens to be, believe it or not, the option that NASA is most excited about. Why? Because you need someone to build it. And those astronauts are getting really bored of going up to the International Space Station. And so this is something they could do. This is actually easier in many ways than going to the moon or going to Mars. Okay, going up to the L2, the Lagrange point, for those of you who know what that is, look it up on Wikipedia later if you don't. Okay, so you go out to like L2, which is really, really far from the Earth, but still, we're still not talking about going out to Mars or anything like that. And at L2, you would basically build this thing. Astronauts would put together this space telescope. That'd be pretty awesome. It'd be a good use of astronauts. And John Grunfeld, for one, approves this idea. He thinks it's awesome. He says, we know how to fix telescopes, and we're willing to do this. We're willing to put our lives on the line to build a telescope like this that can make maps of planets orbiting nearby stars. So that's fine. That's cool. And depending on who wins the election this fall in the US, maybe this might be a pipe dream or something. But in any case, at the very earliest, we're talking like 2030 is when this thing would launch. Mid 2030s. Okay, so that's a while from now. So what do we do between now and then? Well, turns out there's a cool trick. Okay, instead of trying to block out the starlight and look for faint little specks close to, that are not too close to the star, instead you flip it on its head and say, screw it, I don't care about actually seeing these planets. I want to know that they're there, and I want to understand what their atmospheres are like. And it turns out you can actually do that without ever actually seeing the planet. Okay, so that's a while from now. The trick is that they have to be very close to their star. Turns out there's a cool trick. Okay. And so here's a little starry interlude. So the amateur astronomers can look at this and try and recognize the box. Pegasus, the box. It looks like a box that's falling sideways. I'm sure there's like a Latin name for the box or something like that, but I don't know it. So there's Pegasus, and the trick is that they have. So here's the one system I've shown you before, HR 8799b. And so, right, those were those same four planets. Okay, and they're actually orbiting that little dot right at the tip of that arrow, the box. Okay, so now you know where to look. If you want to show your kids. Some of your kids are actually in the audience, and kudos to you for bringing your kids here. But you can show them in the sky once you identify. I'm sure there's like a Latin name for the box. Hey, there are planets orbiting that star. So there's Pegasus. Turns out it's a pretty safe bet to just point at any star and say there's planets. We know the statistics, and your odds are very good, in fact. Okay, but it turns out that a couple years before Christian Marois discovered that system, a couple of Swiss astronomers, Michel Maillard and Didier Queloz, discovered a planet that I can't show you a picture of because it orbits too close to its star. So instead, from here on out, I'm going to be showing you an awful lot of artist's impressions. We know the statistics, and your odds are very good. Okay, but it turns out that a couple years before Christian Marois discovered that system, all right,
a couple
So
of Swiss astronomers.
it's hard to understand how crazy this planet
that I can't show you a picture of
This
because
planet
it's
was
too
so
close to the stars.
unexpected
Instead,
that there
from here on
were
out, I'm gonna show you
competitors
an awful
to the
lot of
Swiss
artists
over in
and
California who had the data to find these planets. Not this particular one, I don't think, but a bunch of other very similar planets. And they're sitting on the data. It never even occurred to them to look for a planet orbiting this close to its star. Okay, this planet goes around its star every few days. And I want to put that in perspective here. So here is our entire solar system and then some. It's on a log scale. Okay, I have to put it on a log scale because otherwise you wouldn't see anything. It would be pointless.
who had the
So
data
the point is, the sun is here, and then you're marching away from the
but a
sun,
bunch of other
Earth
very
at
similar
one
planets.
astronomical
There's
unit.
data. It
Saturn
never
is
occurred
at
to them to
10,
look for a planet orbiting this close to its
and then
star.
you get
Okay, this
to
planet goes
where
around its star every few days.
Eventually get to
And I want to put that in perspective.
And then over
So
here on the
here
right hand side is the nearest star
is our entire solar
Right.
system and then some.
So that's
on a log
a
scale.
huge.
Yeah, I have to put it on a log scale because
And what I want you to notice is one of the empty spots right there.
The sun is here.
Okay. There's nothing in our solar system closer to the sun than Mercury. Right? Mercury goes around the sun every 3 months. It's about 100 days. Okay? It takes Mercury about 100 days to go around the sun. Now, back in the old days when people didn't tweet and they didn't have the internets and they didn't do any of these video games and stuff, they spent a lot of time staring at the stars. And they noticed these certain wandering stars, planets, moving around. And one of them was crazy fast. That one was Mercury. Right? That was the fleet-footed god. Right? Because it went so fast, it was whipping around just 100 days to go around the sun. Right? It takes us 365 days to go around the sun. Right? So it's like more than 3 times faster than the Earth. Right? So there's nothing faster than Mercury in our solar system. Well, it turns out nature is really good at making planets way faster than Mercury, way closer to their star. Okay? So this is the same, basically the same x-axis here. So this is like the stars on the left side, and moving away from the star on the logarithmic scale. Okay? So like Earth is here,
more than 3 times faster than the Earth.
Venus. Mercury is
Right, so
down
there's
here.
nothing faster than Mercury in our solar
But
system.
I've shown you some of the other.
Well, it turns out
Jupiter is there.
Nature is really good at making planets way
Right.
faster.
The y-axis is how massive the planet is. Okay? And so the point is, all of these planets, from 100 days all the way into 10 days, 1 day, shorter than 1 day. Some of these things go around their star in like 6 hours. That's crazy. These planets should not exist. Okay? But nature is really good at making them. Okay? She's not just good at making them, she actually prefers to make them. It turns out it's not that these are freaks, it's that our solar system is a freak. Okay? When you start counting up the planets, you realize that planets like the ones in this black blob here, okay, those planets are actually very common. That's like maybe 50% of stars in the sky have at least one planet there.
But nature is really good
Okay,
at
so that
making
means
them.
they've got a planet that
Okay.
goes around its
She's
star
not
in
just
like
good
a
at
week
making
or
them,
two.
she actually
That's
prefers
actually
to make
totally
them.
normal.
It turns out
Okay, it's like the
not
flip of
that
a coin, whether any given star will have a planet like that.
our solar system is a
What do you think the odds are of having a planetary system that looks like ours?
You realize that
I don't know.
like the ones in this black blob here,
Yeah, you have a guess.
those planets are actually very common. That's like maybe 50.
We actually haven't discovered a single one yet. But you can actually you can extrapolate a little bit, and it turns out to be something like 1 in 100. Could be as high as 1 in 10. Okay, but that's if you're extremely optimistic. Okay, and you're very generous about what you call an Earth-like planet and a Jupiter. Okay, our planetary architecture, the idea of having Jupiter where it is, and then a bunch of rocky planets, and then nothing interior to Mercury is actually really weird. We are the freaks.
We actually haven't
Okay, we don't understand why yet. We don't understand why it's somehow connected to the fact that we have life on our planet. Okay, maybe the fact that we have water on our planet, just a little bit of water, enough to fill the ocean basins, but not enough to drown us all. Okay, maybe that's actually connected to where the planets are in our solar system. Okay, and so these are the sorts of questions people are asking themselves, people who study planet formation, right? Because we now know enough statistics that we can understand where our solar system fits in, and it barely fits in. We are a weird kind of outlier. Okay, that being said, we're weird, but that's okay, because let's just like screw looking at planets that look like Earth. Let's instead look at all these planets that are orbiting very close to their star. Some of those might be interesting, and in fact, some of those might be habitable. And so these are the sorts. This is probably where you got your numbers, right? Is that if you just decide any planet that is the size of Earth and receives about as much sunlight as Earth is like fair game. That's an Earth-like planet to you. Then yeah, there's actually lots of kind of outliers. Lots of. Okay, so how can we characterize it, right? They're orbiting too close to their star to block out the starlight and see the planet. So what do you have to do instead? You do a bunch of trickery. Okay, and so here's the kind of, this is probably where you got your diagram explained it all. So it starts with this one. The transit of the planet passed directly in front of the star. Okay, what are the odds of that? Not very good. But it turns out if your planet orbits very close to the star, it's not so bad. Okay, it's maybe like 1 out of 10. Okay, so you find for every 10 planets you find, one of them will happen to be perfectly aligned, will pass right in front of its star. Okay, so what does a transit look like? You do a bunch of trickery. This is a particularly famous transit. Who here saw this transit? Yeah, I saw it too. I made sure my son saw it. He was like 2.5, 3. I'm not even sure that he saw Venus, but he at least stared at the sun through a big telescope with a filter. It's not so bad. Okay, so that's why every 10 planets you find, one of them will happen to be perfectly aligned. You better hope that we discover immortality or something, because you're unlikely to see the next one. What does the transit look like? But that's okay. This is a particularly. If you look at exoplanets, you actually see transits all the time. So for an exoplanet, a transit looks more like this. Okay, and that's because we don't have pretty pictures of this from stars. Right? We do this for the sun, it's so close to it. But like other stars, they're too far away. So all we get is something that looks like this. You just see how bright, the y-axis is how bright the thing is, and then you're just seeing it go over time. And what you notice is after a while, it gets dimmer for a little bit. It gets dimmer for a couple hours. And the reason it's dimmer is because now there's a little black dot in front of it. And that black dot is a planet. Okay? And so here's my cartoon. Okay? Now I'm going to show you 2 slides. I'm going to keep going back and forth, and I want you to see what's going on. So this is the planet passing in front of the star. Okay, let's say that the planet has an atmosphere that's transparent. So it has an atmosphere that does not block out any light. That's what it looks like. Now, I just turned on the atmosphere. So now the atmosphere is opaque. The atmosphere blocks the light. What happened to the planet? Okay, let me go back. And so here's my cartoon. That's the transparent atmosphere. Now I'm going to opaque atmosphere, right? Keep going back and forth, and I want you to see what's going on. So this is the planet. Earth would never show that. If I showed you Earth, it would be the most boring movie in the world. That would not be good for a public talk. Yeah. So I scaled this up so that you could see it. Now I cheated. Okay. Turned on the atmosphere. So now the atmosphere. So let's try this technique. Okay. Let's look at a planet, and this particular one, GJ1213b. It orbits its star every 1.6 days. So again, I want to emphasize this planet moves way fast compared to Mercury, right? 100 days is nothing. This thing goes around its star in 1.6 days. Okay? And so people looked at it during transit, and what they asked was, does the size of the planet seem to depend on what color of light we observe it with? Okay. In principle, it should. Let's try this technique. Right? In principle, there are certain colors of light where the light will bounce off of things in the atmosphere, like water vapor, for example. Okay, there's water vapor in the air, and it will intercept photons. Okay, that's why water vapor is a good greenhouse gas. So we expect that depending on what color we look at, the size of this planet will be different. People were very disappointed. This is what they got. And all you have to take away from that top plot is that flat line. In principle, there are certain basically a flat line. Okay, that's the planet radius. So basically, they looked at this planet at a bunch of different colors and they said, "Shoot, it's a flat line." Okay, so that meant that maybe it didn't have water vapor in its atmosphere. So they said, "Okay, well let's try something different." So instead of using the very large telescopes on the ground, we used the Hubble. Okay, smaller telescope, but it's in space, so it's actually better for this. And so this was Laura Creedberg's work. So she conveniently plotted in the top part there the gray points for the old data from the ground, and then she got this itty bitty black points, and then she zooms in, and what do you see? Okay, well let's try something different. Okay, and this is problematic because now the flatness of this is the Hubble. It doesn't make any sense. Okay, it is so flat that not only can this planet not have water vapor in its atmosphere, but it can't have carbon monoxide, carbon dioxide, methane. It can't, in fact, have any molecules whatsoever, which is a problem because we know its atmosphere has to be made of molecules because we know its density, we know how fluffy this planet is, and it's got to be made of molecules. And yet there's something in this atmosphere that blocks out all light equally well. Okay, and so that's because the planet, the size of the planet is independent of wavelength, independent of color of light. Okay, so the size is independent of wavelength. That means this planet has something gray in its atmosphere. What do we know that's gray that lives in the atmosphere? Has to be made of molecules because we know it's dense. Birds. We know how fluffy this planet is. And yet there's something in this atmosphere that blocks out all clouds, right? And so this is great. So now we discovered by spending kind of a crazy amount of Hubble Space Telescope time, Laura Friedberg had convinced us all that these planets actually have clouds. The size is independent of wavelength. What kind of clouds, you might ask? Not the same kinds of clouds that we get here on Earth that give us rain. Okay, these are not water clouds. The most likely guesses for what these clouds are made out of is actually more similar to like table salt, sodium chloride. And so it's kind of a weird thought, but that's just, if you figure out how hot these planets are, that's a reasonable cloud to expect. Okay, that's it for transits. Let's talk about eclipses. Okay, so an eclipse is when a planet passes behind its star. We call that being eclipsed by your star. Here, the big bad telescope we can use is the Spitzer Space Telescope. It's the lesser known cousin of the Hubble Space Telescope. Same idea as Hubble, except it's smaller, and it's an infrared telescope, which means it sees like heat radiation from planets. That's a reasonable. Here's our target. This is a planet that orbits around its star for 2.2 days. Let's talk about eclipses. Very fast. Okay, so an eclipse is when a planet passes behind its star. We call that being eclipsed. Here's the movie. Okay, so again, here, if you had like a telescope the size of the solar system, it would be easy, right? You just look at the planet passing by its star. But we don't have that, so all we can measure, except as astronomers, is just the brightness of time. And we see a dip. And then we spend a lot of time trying to understand that dip in like gruesome detail. Okay, we really want to understand the depth of the dip and the shape of the dip and all sorts of stuff. Okay, because this is the only observations we have of this planet. Okay, so again, it turns out the depth of that dip tells you something about the day-side temperature of the planet. Okay, and you can actually do better. It turns out if you look at the shape of the dip, you can actually reconstruct a map of the planet. So you can do a raster scan trying to understand. So you can actually map out the temperature of the day side of the planet. Okay? So this is great. So we've learned something about the day side of the planet, but a planet also has a night side. How can we learn about the night side? It turns out the depth of that dip, you do the phases, right? So now you observe the planet through a full orbit. Now remember, for a planet like the Earth going around the sun, that would be a very boring exercise because you'd have to stay there for like 6 months to watch it go from one place in its orbit to another. But these planets go around their star every few days. And so this is actually totally doable. So I've still sped up the movie because even a few days would have made it really boring. Learn about the night side. So this is sped up. So the point is, when you're seeing the day side of the planet, now you observe it probably looks brighter, looks hotter, right? Because you're seeing thermal heat coming off the planet. And then the night side comes into view, it looks colder. Okay, so we call these the phases, the thermal phases of the planet. Okay, and so this is something that we can now measure for like a dozen planets, if we're generous. Okay, and so based on those thermal phases, we can actually tell you how hot the night side of the planet is. Okay, and so here's a temperature map of one of these planets. Okay, so I guess I should explain the substellar points. The sun is beating down that point right in the very center. Okay, so that's the point that's right underneath the sun. That's the point that's at high noon. The hottest point on the planet is a little bit east of there. Okay, and the hottest point on the planet is about 1,200 Kelvin. It's really hot, right? So for those of you who don't know, at these temperatures, the conversion between Kelvin and Celsius, like who cares? It's still really hot. Okay. So I guess this is hot enough to melt your laptop. It will melt your marshmallow. It will melt everything. It will combust. Okay, so that's the hottest point on the planet. What about the coldest point? Like maybe there's a place on this planet that's actually cool enough that, you know, birds could fly and dolphins could swim. Nope. 900 Kelvin is still extremely hot. Okay, this planet is hotter than the surface of Venus, which, as you all know, means you can melt lead, and probably also some other soft amalgams of things. So this planet is really, really hot.
Okay, so that's the hottest
So
one.
you might not be
What about the
surprised to
coldest
hear
one?
that
Like, maybe there's
astronomers
a
who
place
are
on this planet
really
that's actually
creative, we
cool
call these
enough
hot
that, you know,
Jupiters,
birds could
because they're
fly,
the size of Jupiter,
dolphins could
only
swim.
hotter.
Nope.
So this is a hot Jupiter, and this one, it turns out, if you look at the day side, so at first you're like, wow, that planet's really hot, and that's the correct first impression. But then, upon further reflection, you look at it and you say, not only is that planet really hot, but like, holy cow, the day side is 1200 Kelvin and the night side is 900 Kelvin. That means there's a temperature difference between the day and night of 300 Kelvin. That's crazy, right? So even in the desert on Earth, right, the temperature swings you get between day and night are like,
So this is a hot Jupiter.
10, 20 degrees Celsius, maybe? Okay, so you're talking about hundreds of degrees. And it turns out this is one of the most well-behaved of the planets. Okay, and so I can actually start plotting a bunch of these. Okay, so each oval here, each egg is basically is a different planet. They have really dumb names, I'm sorry. Astronomers, yeah, we name the temperature swings you get. But each of these circles is a different planet. And the planet I just showed you, HD 1897 is the purple egg at the very top of the pile of eggs for Hubble.
Well-behaved.
Okay, and the axis
So I can
here, I've
actually
made up
start
names that
plotting
sort
a
of
bunch
make
of
sense.
these.
Okay, so I apologize. I'm sort of butchering the science a little bit, whatever. So the x-axis is how shiny the planet is, right? So like a charcoal briquette is around here. So actually, a few of these planets are as black as charcoal briquettes. It's kind of curious. There's nothing in our solar system black as charcoal briquette. There's no planets with atmospheres. And then the y-axis is windy. Yeah, it's like how strong the winds are. And the planet I showed you is actually the windiest of the planets. It's the one that does the best job of taking heat and moving it around to the night side. Some of these planets, the one down here, the red one, well, B, that planet has a day side temperature of 3000 Kelvin and a night side temperature of 1000 Kelvin. Okay, so you do some quick arithmetic, yeah, and someone whistle, that's good, that's the right response, right? So you do the math in your head and you say, what? That's 2000 Kelvin temperature difference between day and night, right? And everyone knows nature. Well, what does she abhor? She abhors the vacuum, but she also abhors a really steep temperature gradient in an atmosphere. Yeah, so anyone who understands like fluid dynamics knows that that's crazy. You have a question? It has a day side temperature of 2000 Kelvin, a night side temperature of 1000 Kelvin. Okay, so you do some quick arithmetic, yeah, and someone whistle, that's good, that's the right response, right? So you do the math in your head and you say, well, that's 2000 Kelvin temperature difference between day and night, right? And everyone knows nature. Yeah, you're asking about extremophiles. She abhors the vacuum. Yeah. So temperature gradients in an atmosphere. Yeah. So anyone who understands like fluid dynamics knows that that's crazy. You have a question? Yep. Yep. Absolutely. And even extremophiles would not want to live here. So I have a colleague, Lyle White, who studies extremophiles. He's one of the world's experts on extremophiles, and extremophiles would not want to live on these planets. And it doesn't just have to do with the temperature. It has to do with things like there's no solid surface on the planet. Yeah. So that's kind of a problem, right? So there's no place, there's no like substrate for your critters to live on and do chemistry. So planets this hot you run into a lot of problems. Yep, molecules, absolutely. Most complex molecules don't like to exist at these temperatures. So you have to go to like pretty far-fetched life in order for things to live here. But I am eventually going to get to things that are closer to being habitable almost in my last couple of slides. Okay, so takeaway point from everything I've said so far, we're talking about global climate, right? We're talking about how cloudy planets are, how windy planets are. So we're finally getting to the point where we're talking about in broad strokes about these planets. Okay, we're talking about their global climate. Okay, and we can now do this for dozens of planets. Okay, and this is exciting for planetary scientists, right? Because now we are finally reaching a point where instead of just having the solar system worlds to study, we have lots and lots of other worlds. We have thousands of them that we can start studying. Okay, and so this is sort of like the transition between being a doctor who only studies humans and being a doctor who's also willing to like do experiments on guinea pigs and mice and other, you know, and chimpanzees and stuff like that, because you're like, well, hey, they're also alive, they're kind of like humans, and so maybe I can learn something about how life works by studying these other animals, right? So that's sort of what we're doing. This is how we're learning about planetary science now. Okay, so final couple slides. The James Webb Space Telescope. I have to give this a shout out. It's launching in 2 years. Okay, and actually there's 4 instruments on it, and one of them is actually being built right here. Okay, it's being led out of the University of Montreal. Okay, so René Voyon is actually leading one of the instruments on this, and it's the only instrument that's custom built with exoplanets in mind. So this is pretty exciting. It's a big telescope. What is it going to look at? We don't know, but this is a reasonable target. Okay, these are the Traxxas planets. I hope everyone drank a lot of Belgian beer in the last couple of months in honor of this planet. And actually, very clever acronym on my Belgian colleagues. So they discovered a group of planets, not just one, but a whole fleet of planets orbiting this one star. The star is really small. It's called TRAPPIST-1. Okay, and here's an artist's impression of what it would look like sitting on one of the planets. This is a reasonable target. Looking at your star, and I'm pretty sure this makes no sense, but they're pretending that you can see your star and see your neighboring planets. And I'm pretty sure if you actually did like a proper simulation, that would not be possible. But anyhow, it's cool. And so this is a planetary system. It's kind of like a miniature version of our solar system. Okay, these planets orbit very, very close to their star, but it's okay because their star is very, very faint. What it would look very faint. It's small, it's dim, it's red. So it turns out you can orbit very close to it and still actually have temperate conditions, right? So that's why if you look at this, this is not like methane, it's not lead, this is actually liquid water. But anyhow, it's cool. And so this is a planetary system. Okay, and so we're going to look at it with James Webb. What are we going to see? In our wildest dreams, maybe we could create a temperature map, right? I showed you temperature maps of a hot Jupiter before. We're hoping we can build a temperature map that looks something like this. Okay, and what we'd notice here is the planet has warm night side. Hey, that's not a bad thing. It's like tonight in Montreal. And then there's this weird thing, is that the temperature of the planet as a whole. Okay, so we're going to look at it with James Webb. What are we going to see? We expect to be the very hottest on the planet actually looks cool. We could create a temperature map. Okay, how do you get something that's actually really hot to look cool? We can build a temperature map that looks something like this. Put a cloud on it. And what we'd notice here, right? So those of you who are used to looking at weather maps know that the cold regions on the weather maps are usually the cloudy regions. Okay, and that's because clouds are at high altitude, so they're cold. Same reason it's cold on top of Mount Everest. Okay, and so we might learn something about water clouds on this planet. Okay, and that's curious because it turns out if you come back down to Earth and you think about the problems we have on Earth, such things as global warming, okay, the largest uncertainties we have in global warming have to do with clouds, okay, and how clouds react to different temperatures. And it turns out we can actually start studying clouds on exoplanets. And not only can we study them, but we can actually have people using different global climate models, the exact same models people use for these IPCC reports. We can have them, instead of just making predictions about what's going to happen on Earth, we can have them make predictions of what those TRAPPIST planets are going to look like, and then we can test those predictions with James Webb, right? And so somehow we've gone like full circle back to the planet we live on, the planet we care about. So with that, thanks for your time, and I'll take any questions. Instead of just making predictions about what's going to happen on Earth. Okay, let's start back there. Yep. What those TRAPPIST planets are sure. We can test those predictions with James Webb. Right? And so somehow we've gone like full circle back to the planet we live on, the planet we care about. So with that, thanks for your time, and I'll take any questions. That's a great question. And the answer is mostly you actually take a picture in a fairly limited part of the electromagnetic spectrum, and that's because it's hard to build a detector that can detect all parts of the electromagnetic spectrum. So you have like an X-ray telescope, and you have an infrared telescope, you have an ultraviolet telescope. Even something like the Hubble Space Telescope has a lot of different instruments, right? I can use Hubble, and I can turn on the UV mode, and now I can take ultraviolet images. but I can't do that at the same time as infrared images.
And the
It's,
answer is
you know, in some fantasy land we could do that, but we don't have the technology to do that yet. So yeah, we tend to take images kind of one at a time.
Detect all.
Yeah, there's a question from the kid in the
parts of
front.
the
Yes.
electromagnetic spectrum. So you have like an X-ray telescope, and you have an infrared telescope, you have an ultraviolet telescope. Even something like the Hubble Space Telescope has a lot of different instruments, right? I can use.
Is it all in the observable universe? Yes, it is. And not only is it in the observable universe, it's actually, so if I were to draw, so let's pretend the Milky Way, do you know about the Milky Way galaxy? Yeah, so Milky Way galaxy, let's say it's like big, really, really big pizza pie, like this. Everything I've talked about would fit in like a grain of pepper. Okay, so all the planets I've talked about, they're all right there, all right around where we live in the Milky Way galaxy. Yeah, so there's a lot of planets out there, but for the most part, we can't study them too far away.
It is. And not only is it in the observable universe, it's actually, so if I were to draw, so let's pretend the Milky Way, do you know about the Milky Way galaxy? Yeah, so Milky Way galaxy, let's say it's like big, really, really big pizza pie, like this. Everything I've talked about would fit in like a grain of pepper. Okay, so all the planets I've talked about, all right there, all right around where we live in the Milky Way galaxy. Yeah, so there's a lot of planets out there, but for the most part, we can't study them too far away. It is. And not only is it in the observable universe, it's actually.
Yeah, so you're quite right. It would be more cost effective, and that's exactly what we're doing. So the Kepler mission, so the Kepler mission was the first mission that NASA launched where the goal was just to count planets. Okay, and so that's sort of like making a census. It's like you're making a census of like what kinds of planets are out there. And so in that case, you don't actually really care whether those planets are in your backyard. You just want to know what kind of planets are out there. Now that we know what kinds of planets are out there and we can start doing statistics, we say, holy cow, there's a lot of planets out there, and there's actually a lot of planets that are kind of like the Earth in the sense that they're probably rocky and orbit the right distance from their star. Most of them happen to orbit around red dwarf stars. And so now there's dedicated missions being launched. The next one is TESS, that are dedicated for finding the very nearest planets, especially orbiting red dwarf stars. And there's a lot of ground-based efforts to do this. And we can only do that now because we know the statistics. We know these planets are very common. It would have been a shot in the dark there, but now it's like, it's a safe bet.
Planets that are kind of like the Earth in the sense that they're probably rocky.
Okay, fine. You in the white. Okay, the guy in the. Yeah, you first. Okay, good.
That are dedicated to finding the very nearest planets, especially orbiting red dwarf stars.
Yeah.
There's a lot of ground-based efforts to do this. And we can only do that now because we know the statistics. We know these planets are very common. We're going to shot in the dark, but now it's like it's a safe bet.
Yeah, it's a great question. So people call these rogue planets or Steppenwolf planets. We think they exist. The way we think that we detect them, and I say think because you'll understand, it's kind of indirect, is basically we don't actually see the light from the planet. What we do is you look at a background star, so you're just looking at a bunch of random stars, and then occasionally one of them gets brighter momentarily for a couple weeks. Okay, so that's weird. Why did it get brighter? Well, it turns out if you look at the shape, the way in which it got brighter, it's consistent with gravitational microlensing, which basically means some foreground object, an unseen object, passed between you and that distant star, and it bent the light, right? Einstein says that happens, and we don't mess with Einstein, right? The year the gravitational wave detected, right? So the light is bent, and it actually focuses. It acts literally like a lens. And so that's called gravitational microlensing. And actually the W first mission that I mentioned at some point in my talk, the main exoplanet goal is actually to do gravitational microlensing. It's going to detect thousands and thousands of planets by basically staring at stars and then seeing these faint things pass in front. And so based on microlensing experiments, we actually think that there's about as many free-floating planets as there are stars.
And it actually focuses. It acts literally
like crazy, right? That means planet formation is messy business, right? It means for every like beautiful, harmonious planetary system you see, there was like some sort of black sheep planet that just got launched out. Yeah, there's some lonely planets out there.
And then seeing these faint things pass in front.
Yeah, and so based on microlensing experiments, we actually think that there's about as many free-floating planets as there are stars. Yeah, crazy, right? That means planet formation is messy business, right? It means for every like beautiful, harmonious. Yeah. So the size of the stars is something think, so for the most part, we astronomers like to pretend, oh yeah, we know how to do stars. We've been doing stars for hundreds of years. Don't worry about the stars. And that's usually true. So for the most part, the size of the star is actually not a challenge. If you tell me the color of a star, I can tell you how big it is, for the most part. Turns out that's not always right. And in particular, red stars, you can really screw it up. And so this has actually been a problem. Occasionally people have discovered planets orbiting a red star. They thought it was a red dwarf. It turned out it was a red giant, right? So the planet that you thought was like a small Earth-like planet orbiting a small red dwarf is actually a giant planet the size of Jupiter orbiting a red giant star. And so that happens occasionally. It's comical. People are embarrassed by it, but it doesn't happen that often, believe it or not. So we have stars pretty dialed. You can really screw it up. And so this has actually been a problem. Occasionally people have discovered planets orbiting a red star. They thought it was a red dwarf. It turned out it was a red giant, right? So the planet that you thought was like a small Earth-like planet orbiting a small binary stars. Thanks for asking that. Yeah, I didn't mention binary stars. Yeah, so most of you know, you certainly know, that the stars, the dots you see in the night sky, most of those are actually binary stars. Right? They're two stars orbiting each other. They're just so close you can't separate them. Okay, and so you might think, well, geez, if you had like an egg beater like that in the center of your solar system, surely that makes it hard to live in that solar system. It makes it hard to orbit around it. Turns out it's not a problem. Okay, and we've actually found lots of planets orbiting binary stars. And you find them in the most weird things. You can find like two stars going around each other and a planet outside. You can find two planets, there's a star and a planet going around it, and then another star up here. You can find two stars, a planet, and then another star. Like every possible combination, right? So planets don't care. Egg beater like that. Like honey badger, surely it's hard to live in that so you find planets everywhere. Yeah, in the back with the cowboy hat. Okay, and we've actually found lots of planets orbiting binary stars. And you find them in the most weird things. Are there binary planets? Oh! You find two planets. Turn off your Twitter. There may be binary planets. There may be a binary planet in the Traxxas system. Don't tweet. Yeah, so you find planets everywhere. Yeah, in the back with the cowboy hat. And we've actually found lots of planets. Yeah. Oh, yeah. Are there binary planets? Yeah, so we usually assume, this is one of these like dark secrets. So we usually assume that the length, that basically the planet's rotation is perfectly matched with its orbit so that you have a permanent day hemisphere and permanent night hemisphere. But we assume that. We actually have very little evidence that that's actually the case. We assume that because most planets I talked about orbit very close to their stars, which means that the tidal forces are strong, so the planet gets kind of football shaped, and based on everything we think we know about planets, the planet's rotation should slow down and eventually it'll be locked. So just like we always see the same side of the moon, right? To see the far side of the moon, we had to get the Soviet Union to send a probe and look at the far side of the moon. So likewise, the idea is that these planets have a permanent side that's always facing their star. That's what we assume. There are some clever ways of checking it. Most planets I talk about orbit very close to their stars, which means that the tidal forces are strong, so the planet gets kind of football shaped. And based on everything we think we know about planets, the planet's rotation should slow down and eventually it'll be locked. So just like we always see the same side of the moon, right? To see the far side of the moon, absolutely. Yeah. So like the plot I showed you, that scatter plot showing planets, like where planets lie, is heavily skewed by the kinds of methods we've used. That will improve with, for example, the microlensing. The microlensing technique actually fills out a nice part of that diagram that was pretty empty. So yeah, different ways of finding planets are good at finding different kinds of planets. And so that's why you want to just kind of like fire on all cylinders and just try lots of different methods. But you're quite right. And that makes it hard. If you want to do serious science, you can't just look at one of those plots and kind of eyeball it and say, yeah, I think there's a bunch of planets there. It doesn't actually work. You have to do some math and account for the way in which people have detected planets. So that biases it. The microlensing technique actually fills out a nice part of that diagram that was pretty empty. So yeah, different ways of finding. Oh, how did the planets get loose? Yeah, the free-floating planets. So the question: how the heck did they get loose? Right? There's a lot of gravity holding our planets to the sun. Well, you're quite right. So the answer is something violent happened between two planets. Okay, so two planets got too close to each other. One of them, so you think the planet that got the short end of the stick is the one that got launched out and is now a lonely planet, but maybe not, because what happens to the other planet most of the time, people have simulated this on computers, is the other planet goes into the sun, dies. Yeah, so you know, you can either live a life of loneliness among the stars, or you can just die.
So the answer is something violent happened between two
Yeah, you.
planets. Okay, so two planets got too close to each other. One of them, so you think the planet got the short end of the stick because the one that got launched out and is now a lonely planet. But maybe not, because what happens to the other planet most of the time, people have simulated this on computers, is the other planet goes into the sun, dies. Yeah, so, you know, you can either live a life of loneliness among the stars, or you can just die.
Yeah. Yeah, you. Yeah, so it's always easy in hindsight, right? So this is called like post-diction, right? So in science is all about prediction, right? It's like if I come up with a hypothesis, if I think my hypothesis is correct, I'm going to put my neck out and I'm going to say these are some predictions, all right? And then people will go and test my predictions, and most of the time they will find that they're wrong, and then so much for my hypothesis, right? If my predictions are correct, then it gets promoted to being a theory, and then people take it more seriously, but then they're constantly trying to disprove it anyways, right? You look at something like the theory of gravity, general relativity, people are always trying to disprove them anyways, right? That's what scientists do. We try and break theories. That's our job. Right? That's where we get job security, by constantly breaking theories and having to develop new ones. So the problem with most, if you go back and you look at like ancient texts, you can usually find bits and pieces of them that do seem right in hindsight, but for the most part, their predictive power is actually pretty dismal. Like you'll find, you know, maybe 1 out of 100 is correct or something like that, but it's actually pretty bad compared to the body of science. And so most scientists would say, yeah, you know, you can come up with some hypothesis. Someone before the invention of telescopes maybe guessed at something and occasionally was correct, but it didn't have a very good track record. It wasn't the kind of thing you'd be willing to bet money on.
Do seem right in hindsight, but for the most part, your predictive power is actually pretty dismal.
Like you'll find, you know, maybe 1 out of 100 is correct or something like that, but it's actually pretty bad compared to the body of science. And so most scientists would say, yeah, you know, you can come up with some hypothesis. Someone before the invention of telescopes maybe guessed at something and occasionally was correct. So you need rocket scientists. You need smart people to do these things. Money. Yeah, so the problem with a lot of this, and this is true generically of science, so I can tell you a few anecdotes actually about this. So okay, so the short answer is some of this stuff is classified technology. That's the short answer. That's often a problem in astronomy. A lot of what we do turns out looking up at the stars, not that different from looking down at the Earth, trying to see objects. So some of you who are, you know, who follow the news very closely might know that the W1 mission, I've alluded to a couple of times, the mirror for that was actually gifted to NASA by the spies. So it was a spare sitting in a warehouse. They had no need for it. They actually had multiple spares. Okay, and when you have a spare of something, it's like if I have a spare tire, and I no longer need my spare tire, that's because I now have like a monster truck that those tires don't fit on, right? And so basically, the expectation is that the spies already have things like the James Webb Space Telescope looking down at us, right? But there's technology there that people know how to do it, but the problem is it's not written down, right? If you have beers with people who work in aerospace, some of them swing both ways. So they do dark side technology and they do science. And they actually, dark side is not a joke. It's actually what they call it. And they'll be like, oh yeah, I think we can do that. You know, building a telescope in space, it's not crazy. And you're like, okay, it's good to know. Right? If you have beers with people who work in aerospace, some of them swing both ways. So they do dark side. The furthest planet, it'll be a micro-lens planet. So this would be halfway to the ball. Actually, dark side is not a joke. It's actually what they. It's like 8,000 parsecs. So that's like 24,000 light years. Half-life to 12,000 light years. Any of the grad students can correct me if I screwed it up. Yeah.
for this planet, it'll be a microlens. This would be halfway.
Oh gosh.
Actually, dark side. So
You know the answer. To 200? 100 AU. 100 times the distance to the Earth. There you go. See, we just crowdsourced the answer. What was your second question? Yeah, there is. So if you visit the Jet Propulsion Lab in Pasadena, you'll see very modern things. Like you'll see they have a sand pit where they practice their rover maneuvers and stuff like that. You know, like remember I told you these rovers, if they flip over, it's a big problem. So then they'll actually make mock-ups. Like when they get stuck someplace on Mars, they make a mock-up in Pasadena at the Jet Propulsion Lab, and then they actually try and test things out. And of course, it's kind of problematic because they're testing it out in higher gravity than you have on Mars, but they try and fake it. So you have very modern things, but it turns out, just like a couple of buildings over, you have people still working on abortion machines. They come in from time to time and kind of like, you know, ping it, still alive. Yeah, so it's like, you know, it's a small, there's no one working full time. Like when they get stuck someplace on Mars, they make a mock-up in Pasadena at the Jet Propulsion Lab, and then they actually try and test things out. And of course, it's kind of problematic because they're testing it out in higher gravity than we have on Mars, but they try and fake it. So you have very So the cool stuff going on with the moons is what is generically called the icy moons, right? So there's like Europa, which has liquid water under the ice. Enceladus has these geysers coming out of the ice. And so there are moons in our solar system that are actually, from an astrobiology standpoint, are very interesting. And there's actually talk of sending a mission that could fly through the plume of Enceladus to go through the geyser and actually do some biochemistry on it and just see whether there's organic molecules. So those are currently the moons that are most exciting from a biological standpoint, are the ones that have liquid water under the ice. Geysers coming out of the ice. And so there are moons in our solar system that are actually, from an astrobiology standpoint, are very interesting. And there's actually talk of sending a mission that could fly through the plume of Enceladus to go through the geyser and actually do some biochemistry on it and just see whether there's organic molecules. So those are the planet is formed like a donut. So I don't know of any planets shaped like donuts. There are protoplanetary disks shaped like donuts, right? So sometimes you'll see images where you block out the starlight and then you see a donut around it, but that's just like a band of material that does have to do with planets. Usually the reason you get that band of material is because there are planets sculpting that thing. But no, there aren't any. So planets, all the planets we can detect on other stars are also big that they're spheres, they're spherical. Some of them are a little bit football shaped because they're so close to the star. So kind of like rugby to football shape, that's totally legit. Donuts, no way. Sometimes you'll see where you block out the starlight and see a donut around it, but that's just like a band of material that does have to do with planets. Usually the reason you get that band of material is because there are planets sculpting that thing. But no, there aren't any. So planets, the first one I'm going to punt on, but you can Google it later. How fast does a hot Jupiter go? I don't know. It's really fast. But I mean, even Earth goes really fast, right? It goes like way supersonic, right? But you don't feel it because the entire planet's moving, so who cares? But no. If it was passing through something, absolutely. But it's going through space. Space is empty. So it's okay. No, that's the saving grace. So people used to tear their hair out back in like ancient times about this, right? This is why the Greeks were like convinced, like, no, that's crazy talk. Like, how could the Earth possibly move around the sun? Like, shouldn't we all like notice it? Or like the Earth spinning on its own axis? We'd all get flung off, right? And that stuff is like, it's almost correct, except it's just missing usually a little bit of physics. And it turns out the Earth is going really fast through vacuum, so we don't feel a thing. But it's going through space. Space is empty. So it's okay. No, that's the saving grace. So people used to tear their hair out back in like ancient times about this, right? This is why the Greeks were like convinced, like, no, that's crazy talk. Like, how could the Earth possibly move around the sun? Like, shouldn't we all like notice it? Or like the Earth spinning on its own axis? We'd all get flung off, right? And that stuff is like, it's almost correct, except it's just missing usually a little bit of physics. And it turns out the Earth is going really fast. So I will give you one other example. Here. No, that's the saving grace. right? So if you could make a map like that of another planet, you could figure out that it has continents and oceans. That would be interesting, because we don't understand why Earth has continents and oceans. Earth has plate tectonics. We don't really know why Earth has plate tectonics and other planets don't, right? We have no predictive theory, to go back to the gentleman's question back there. We have no predictive theory for plate tectonics, right? People used to think they had a predictive theory, and they made predictions and they're wrong. So now we're back to square one. And so we don't understand how plate tectonics works. We don't understand why the amount of water we have on Earth perfectly fills the ocean basins and doesn't drown us. You know, we have a lot of water stuffed in the interior of our planet. We don't quite understand how our cycles govern it. Just being able to take images like this of another planet would help understand the geochemical cycles happening on Earth. So that's another. We have no predictive theory for plate tectonics. Right? People used to think they had a predictive theory and they made predictions and they're wrong. So now we're back to square one. And so we don't understand how plate tectonics works. We don't understand why the amount of water we have on Earth perfectly fills the ocean basins and doesn't drown us. You know, we have a lot of water stuffed in the interior of our planet. We don't quite understand how our cycles govern it. Just being able to take images like this of another planet would help. I wouldn't be surprised if this exists.
Yeah, it exists. I don't think you can get it for free. All of the free planetarium software tends to be looking out. Maybe Celestia, you could do that. I don't know if Celestia does that.
Yeah, so I know there used to be when I was a grad student, we had a program that did that. It was based on the Sloan Digital Sky Survey, so it would have been proprietary. And you had to run it on a supercomputer so that you could, because there's just too many stars. I mean, you should probably use some way to turn off the stars, but if you don't turn off the stars, it's just like the gajillions of stars, right? So you're trying to like change your viewing angle and it crashes your computer.
Planetarium software tends to be looking out. Maybe Celestia, you could do that. I don't know if Celestia does that.
Yeah, so I know there used to be when I was a grad student, we had oh, that's a good question. It's missing one key ingredient, oxygen. Yep. Yeah, so if you went there, so it'd be really dangerous to get like an astronaut who went there with an oxygen tank, and he could have a leak, and he could have a really catastrophic disaster. Yeah. For sure. Yeah. So this big telescope on the right, which people now call Rouvoir, the goal of this telescope is not actually to build those cute maps I showed you. That's like my very biased thing I think would be awesome to do with them. The goal of this is actually to look for biosignatures. So the goal of this is to look in the spectra of these planets and look for things like ozone, which is indicative of oxygen, methane, things like that, things that are produced by life on Earth. Sure. Whether it would conclusively tell you that it's life is a can of worms, but it would give you very interesting not actually to build those cute maps I showed you. That's like my very biased thing I think would be awesome to do with them. The goal of this is actually to look for biosignatures. The goal of this is to look in the how many planets by the Doppler method? A couple hundred, something like that. Yeah. So the number, it was definitely the leading method for a long time, and then it got superseded by transits. But the Doppler method is still crucial. So basically, anytime someone detects a planet with transits, you then have to weigh it using the Doppler method. So the Doppler method is still crucial. So actually, again, my colleagues on the other side of the hill at the University of Montreal are building instruments to do this, to be able to weigh the planets orbiting low-mass stars, these red dwarfs. So it's a very important measurement to make. A couple hundred? Well, let's hear from you again. It was definitely the leading method for a long time, and it got superseded by transits. But the Doppler method is still crucial. So basically, anytime someone detects how many planets have been discovered? It's close to 6,000 right now. Yeah, it's a lot. I know it's a lot. And probably by the time you're my age, it's going to be like tens of thousands. Yeah. The planets orbiting low-mass stars, these red dwarfs. How many are rocky? Ooh, that's a good question. Like hundreds are rocky, but a lot of them are like still, they're not nice places to live. They're like rocky, but they're like molten rock. How many are discovered? It's close to 6,000. How many more questions, maybe?
Like a couple.
A couple? Okay, let's hear from you back. Yeah, and probably by the time you're my age, it's going to be like tens of thousands. Yeah. How many are rocky? Ooh, that's a good question. Like hundreds are rocky, but a lot of them are like still, they're not nice places to live. They're like rocky, but they're like molten. Oh, yeah. That's a great question. So in other words, maybe we just got lucky or unlucky or something, and just all the ice balls we saw were orbiting in a certain way. Yeah, so people try to account for that. And they're pretty certain you'd have to be crazy, crazy unlucky for that to be the case. But it's an area of active debate, very active. There are constant papers. Okay, even further in the back. Last question. Yeah,
A lot
you.
of them are like still, they're not nice places to live. They're like rocky, but they're like molten.
Oh, yeah. That's a great question. So in other words, maybe we just got lucky or unlucky or something, and just all the ice balls we saw were orbiting in a certain way. Yeah, so people try and account for that. And they're pretty certain you'd have to be crazy, crazy unlucky for that to be the case. It's an area of active debate. Yes, the ages of solar systems. So the short answer goes back to the gentleman's question about stars. Someone here asked about like how do we know the size of the stars or something like that. And the answer is don't worry about it. We've been doing this for a long time. So when we look at a star, we can tell you how old it is. We have fairly large uncertainties. We'll say it's like 5 billion years old, plus or minus 4 billion years old. But that turns out it's good enough. The point is, it's billions of years old. So that's the first part of the answer. And the second part, for like how do we know the evolution of these systems? We don't, right? So we're in exactly the same boat as a paleontologist who just finds dinosaur bones and has to try and reconstruct what the heck the dinosaur would eat for lunch, right? So we see a planetary system, we see where it is now, and we have to totally do some guesswork to figure out how it got to look like that. Like when we find these planets really close to the star, how did they get there? We couldn't have formed billions of years old, right? So it's a big mystery.
Okay, so I guess we're going to cut off questions now. Thanks for going to stick around, I guess, if you want to.
We don't, right? So we're stuck. We're in exactly the same boat.
Everyone else, we're going to have our telescopes out. We're observing Jupiter and Saturn.
We see a planetary system. We see where it is now,
and we have to totally now, so it should be getting darkish enough to see things. So if you'd like to look through our telescopes, take the elevators down to the ground floor, and we're in a little grassy area outside. I guess we're going to
Why are there more gas giants and rocky planets? There aren't. There's actually a lot more rocky planets. It's just that